Welcome back, Focus Learners, to another edition of The Explainer. Today, we're unlocking the hidden architecture of the universe. Now, we often think of chemistry as this kind of abstract world, just letters and numbers on a whiteboard. But honestly, the atomic world is the literal blueprint for every single physical material we interact with every day. The rules of how tiny, invisible atoms stick together, well, they dictate the shape, the strength, and the behavior of our entire world. So let's just dive right into a real-world mystery. Why does water, the stuff we drink every single day, boil away into a gas at just 100 degrees Celsius, while a diamond, a solid rock, needs a staggering 3,500 degrees just to melt? To wrap our heads around this massive difference, we've got to take a micro to macro journey. We need to zoom all the way down into the hidden architecture of atoms to see exactly how they connect. Which brings us to Section 1, the art of sharing and finding stability in the atomic world. You see, most atoms out there are naturally a bit unstable, and they desperately want a full outer shell. To solve this little problem, nonmetal atoms actually team up to form a covalent bond. Basically, this is a super strong bond formed when two nonmetal atoms share a pair of electrons to get that full outer shell. Now, unlike ionic bonds where electrons are completely handed over from one atom to another, covalent bonds are all about sharing to reach stability. It's a true partnership. And there's this incredible physical tug-of-war happening right before our eyes. This bond isn't just some magical line connecting two circles. It is a real physical force. Think about the electrostatic attraction happening here. We've got the positive red nuclei of the two atoms on the outside, and smack in the middle, in that overlapping space, are the blue, negatively charged shared electrons. Both of those positive nuclei are highly attracted to that shared negative center. It's literally this mutual attraction to the shared electrons that holds the atoms so tightly together. Moving right along to Section 2, blueprinting the invisible, let's talk about dot and cross diagrams. To map out these invisible partnerships, chemists rely on dot and cross diagrams. Take the blueprint for a super familiar molecule, water, or H2O. Let's break it down. Right in the center, we have the larger oxygen atom. Now, oxygen naturally has 6 outer electrons, but it really wants 8. So what does it do? It shares one pair of electrons with a hydrogen atom on the left and another pair with a hydrogen atom on the right. Notice how the shared electrons, represented by one dot and one cross, sit perfectly inside those overlapping circles? Thanks to this clever sharing, the hydrogens get their full shell of 2, and the oxygen gets its full shell of 8. Boom, everyone's stable. And then we have carbon, which brilliantly illustrates the ultimate team player, maximizing its sharing. Take methane, or CH4. Carbon starts with 4 outer electrons, meaning it needs 4 more to hit that stable 8. So it forms 4 distinct single covalent bonds with 4 different hydrogen atoms. It is this perfectly symmetrical sharing arrangement that creates a highly stable, tight little molecule. All right, Section 3, simple molecular structures, or as I like to call it, the tale of small cliques. So you might be wondering, how do these tiny molecules interact with each other when they're all grouped together? Well, the crucial thing to grasp here is a major distinction. Think of a simple molecule kind of like a tightly knit family unit. The covalent bonds holding the atoms together inside the molecule, absolutely incredibly strong. But that family doesn't really interact much with its neighbors. The forces between the different molecules, which we call intermolecular forces, are actually surprisingly weak. And this completely explains why things like water or chlorine boil so easily. When you heat up a simple molecular substance to turn it into a gas, you are absolutely not breaking the strong covalent bonds holding the atoms themselves together. The atoms don't split apart from each other. Nope. You're really just supplying enough energy to overcome those weak, neighborly intermolecular forces so the whole molecules can just drift apart. We can see this brilliantly illustrated in the halogens. Think about this trend for a second. Chlorine boils at a freezing -34 degrees Celsius. Bromine jumps to 59 degrees, and iodine all the way up to 184 degrees. So why the massive jump? Well, as we go down the group, the atoms, and therefore the molecules, get physically larger. And as molecules get bigger, those intermolecular forces between them get stronger. Stronger forces between the molecules literally just means you need a lot more heat energy to break them apart. Welcome to Section 4. Giant covalent lattices, the grand architecture. Now, what happens when the sharing just never stops? When it forms an endless, repeating grid instead of a tiny little clique? Well, you get a diamond.
In this structure, there are no separate small molecules at all. Every single carbon atom is covalently bonded to 4 other carbon atoms, which are bonded to 4 others, creating this massive, continuous 3D lattice. Because every single connection is a super strong covalent bond, diamond is the hardest natural solid on Earth. To melt it, you'd have to break millions of strong covalent bonds all at once, which, as you can guess, requires an absolutely massive amount of feed energy.
Now let's compare that priceless gem to something a little more everyday, like beach sand or silicon dioxide. Despite one being incredibly valuable and the other being literally everywhere, structurally they are remarkably similar. Both of them are giant covalent structures. While diamond is pure carbon, silicon dioxide features silicon covalently bonded to 4 oxygens in a very similar tetrahedral shape. And because of this shared giant architecture, both of them possess extremely high melting points and neither can conduct electricity. The blueprint dictates the physical reality, right? Which brings us perfectly to our final chapter, Section 5, the electric exception, and the rules of conductivity.
We just noted that diamonds and sand don't conduct electricity at all. In fact, to conduct electricity, a material has to pass a pretty strict test. It must have charged particles, like electrons or ions, that are actually free to move around. And simple covalent molecules? They fail this test completely. They share their electrons perfectly in closed loops, meaning there is no overall electric charge, no free electrons, and definitely no free ions to carry a current.
But hey, nature loves to throw us a curveball. We know carbon can bond to 4 other atoms, just like we saw in a diamond. But what if a carbon atom only bonds to 3 other atoms instead of 4? What kind of structural anomaly does that create? It creates graphite. And there's a crucial quote from our sources here that sums it up perfectly. Each carbon atom in graphite has 1 spare electron. This electron becomes delocalized. Since carbon naturally has 4 outer electrons, but is only using 3 to bond in this scenario, that 4th electron is just left over. It's essentially a free spirit. It becomes delocalized, creating this sea of free-moving negative charge throughout the entire structure. Because these electrons can actually move around, graphite can freely conduct both heat and electricity. Pretty wild, right? And that is not the only difference. Because graphite is bonding in 3s, it actually forms flat hexagonal layers. Inside the layers, the covalent bonds are incredibly strong, but between the separate layers, the forces are super weak. This means the layers can easily slide right off each other. It's exactly why graphite is soft, slippery, and makes for the absolute perfect pencil lead. Oh, and by the way, scientists can isolate just one of these single layers, a material you might have heard of called graphene, which is literally revolutionizing modern electronics as we speak. So I want to leave you with this final provocative thought. Both diamond and graphite are exactly the same element, pure 100% carbon. Yet, if just one rearranged electron and a slightly different sharing pattern can change soft, gray, conductive pencil lead into a rigid, transparent, insulating diamond, what other incredible secrets and materials are hiding right now in the unseen atomic bonds of the world around us? Keep learning, keep questioning, and I'll catch you in the next Explain.